So let me open the notes. Okay. So today, as I have already mentioned, we will start with discrete time Fourier transform. Previous week, we have seen the Fourier series representation for discrete time periodic signals. Now, today we will continue our discussion with aperiodic signals, aperiodic discrete time signals that can be represented in Fourier series representation. So, discrete time Fourier transform is actually, as in the case of continuous signals, helps us to represent aperiodic signals in Fourier domain. And the discussion starts similar to the continuous case. What we do is this: we first start with this x of n, and this x of n is an aperiodic signal. Then we try to make it periodic by simply repeating it for the period n, and then actually the relation between x tilde of n and x of n is this. X tilde of n is nothing but the periodic version of x of n, and you simply shift x of n to the right and to the left with integer multiples of n. So if you do this, actually you obtain your periodic signal x tilde of n. So first, let me start with writing the Fourier series synthesis and analysis equations. So let's write x tilde of n. Since x tilde of n is periodic, I can write it in Fourier series form. So k from some k0 to k0 plus n minus 1. So remember, if the important thing is here is this. This summation has the length of n. The starting point is not important. So I start from, let's say, a generic starting point k0, then a k e to the power jk 2 pi over capital N n. So this is the well-known synthesis equation. You know this very well. So what about the analysis? So ak is obtained as, remember from previous week, summation n from some, let's say, n0 to n0 plus n minus 1, x tilde of n e to the power minus j 2 pi over capital N kn. So this is my case. So in our case, since x of n is in this interval, what I will do is I will write it as summation 1 over n, summation n from minus n1 to n2, let's say, x of n, x tilde of n e to the power minus j 2 pi over n kn. So x of n is in this interval, so I take the summation within a discrete, let's say, period. It can be this period or that period or that period, whatever I wish. But the important thing is this summation is actually evaluated within an interval of length capital N. So since x tilde of n is non-zero within a period apart from this interval, to simplify things, I change the limits to minus n1 to n2, and this is my case. So if I continue, this is nothing but 1 over n summation n from minus infinity to plus infinity x of n e to the power minus j k 2 pi over n. So x of n is non-zero except this interval, so I can for sure extend the limits to plus minus infinity because it is only non-zero within this interval. X of n is non-zero within this interval, so I can extend the limits to plus minus infinity. So then I define this. Let me define x of omega as summation n from minus infinity to plus infinity x of n e to the power minus j omega n. And if I define this, then ak is nothing but 1 over n x of omega evaluated at omega equals k 2 pi over n. So I have defined this x of omega And based on this x of omega, I can simply define AK as follows. So here there is a trick. You have x of n, which is aperiodic. Then you make it periodic by repeating it with k, with let's say by shifting it by k amounts, multiples of n into the multiples of n amounts. Then you define this x of omega, but this x of omega is based on x of n, the aperiodic version. And once you sample and or evaluate this x of omega at specific instance, omega equals k 2 pi over n at those points, then you find the Fourier series coefficients for the periodic version, which is x tilde of n. So this is an interesting, let's say, observation. So let me continue by rewriting x tilde of n. If I rewrite x tilde of n, it is summation k from some k0 to k0 plus n minus 1 over n x of, by the way, this is capital X, so this is this x here, okay, this x of omega, x of k 2 pi over n times e to the power j 2 pi over n kn, and this equals to nothing but 1 over 2 pi summation over k x of k 2 pi over n e to the power j 2 pi over n kn times 2 pi over n. So I have put it here a 2 pi in denominator and a 2 pi here in numerator. So it is almost the same. So if I define, let's define 2 pi over n as omega 0. If I define this, then x tilde of n is equal to 1 over 2 pi summation over k x of k omega 0 e to the power j omega 0 and k times omega 0. So this is my x tilde of n. I did nothing but change the variable. So as n goes to infinity, I know that for sure x tilde of n is going to x of n, because those parts are separated far away, so there is infinite difference. Let's say they are infinitely many apart. Those samples or those let's say x of n parts are separated infinity away. So as n goes to infinity, x tilde of n is going to x of n. And in this case, x of n, simply the summation is going to, again, some integration. This n is going to infinity, so this omega 0 is nothing but my differential element, the omega. So x of n is simply 1 over 2 pi integral over a 2 pi period, x of omega e to the power j omega n d omega. So it tells me that, so by the way, it is also written here. It tells me that actually, if I define this x of omega as I defined here, if I define this x of omega, then it turns out that as a capital N going to infinity, I can reconstruct x of n from x of omega. So this gives me the actually discrete time Fourier transform pair in time domain and in frequency domain. So x of omega, by the way, this derivation is just for mathematics, so you should follow these steps, but the result is more important for us, which is this, let's say, a discrete time Fourier transform pair. X of omega is called the discrete time Fourier transform of x of n, or it is called as the discrete, or it's called as the spectrum of x of n. These are called as well synthesis and analysis equations. The discrete time Fourier transform x of omega is periodic with 2 pi, so you can check it easily. So let's calculate x of omega plus 2 pi. So what is this summation n from minus infinity to plus infinity? X of n e to the power minus j omega plus 2 pi n. Actually, I'm just using this equation and putting omega is omega plus 2 pi. So this is equal to summation n x of n e to the power minus j 2 pi n e to the power minus j omega n. Of course, this is equal to 1, so this is equal to x of omega. So x of omega is periodic with 2 pi. Well, if you compare discrete time Fourier series and discrete time Fourier transform representations, actually both represent signals as a linear combination of complex exponentials. So discrete time Fourier series, for discrete time Fourier series, actually complex exponentials occur at a discrete set of harmonically related frequencies. Remember the synthesis equation, actually it was a summation term instead of integration. But in discrete time Fourier transform, complex exponentials occur at a continuous frequencies over any continuous interval of length 2 pi and have amplitude x of omega over 2 pi. So it is here. So instead of a summation, now you have, let's say, an integration. So you integrate this continuous x of omega over omega in order to find x of n. But in a Fourier series case, this was a summation, so we were summing discrete set of harmonically related frequencies. Well, from the development of discrete time Fourier transform, the discrete time Fourier series coefficients ak of x tilde of n are nothing but equally spaced samples of discrete time Fourier transform of x of n. So it is already here. So from if you have x of omega, so the Fourier transform, discrete time Fourier transform of the aperiodic version, you can find the Fourier series coefficients AKs for the periodic version by simply sampling at those specific points. So what about convergence? Actually, just like the continuous time Fourier transform, discrete time Fourier transform exists if either of those are satisfied. X of n has either finite power or it is absolutely summable. So if either of those conditions are satisfied, then you can say that your discrete time Fourier transform exists. Well, here we have a note. Discrete time Fourier transform synthesis equation is integration over finite periods. So we do not have a convergence issue with it since it is integrated over a finite interval. So here I have a simple example. X of n is given as a to the power n u n, and a is in the interval 0 to 1. Compute x of omega and plot its magnitude and phase. So let's write x of omega. It is simply using the well-known relation e to the power minus j omega n. This is equal to summation n from minus infinity to plus infinity a n u n e to the power minus j omega n. I can easily change the limits to n from 0 to infinity since there is un here. A to the power n e to the power minus j omega n, and this is summation n from 0 to infinity a e to the power minus j omega to the power n. And this is nothing but 1 over 1 minus a e to the power minus j omega. So I can write it as this, if you wish 1 minus a cosine omega minus j sine omega using Euler's relationship. So when let's say omega is 0, it means that sine 0 is 0. So here I have 1 over 1 minus a. So please note that x of omega is again a complex number in general. So this is why we are asked to find its magnitude and phase. So for omega equals 0, for omega equals 0, omega equals pi, omega equals, let's say, k pi, 2p, pk. For all of those cases, actually, here I have x of omega is a purely, let's say, real number. It's not imaginary for those omega values. So phase is 0 for omega equals 0 or pi or 2 pi minus pi, whatever you wish. So let me plot its magnitude and phase here. First, I will plot the magnitudes. It is only enough to plot for minus pi interval, because you know that it's periodic. So it is just like this. So the peak value is 1 over 1 minus a occurring. So by the way, this is norm of x of omega. This is omega, and it is 1 over 1 plus a. So the maximum value is occurring at 0, and the minimum value is occurring at pi or minus pi. So at omega equals pi, it is clear. For omega equals pi, cosine pi is -1, so you have 1 over 1 plus a. So this is the minimum value for the norm. For omega equals 0, you have 1 over 1 minus a, and this is the maximum value. So this x of omega oscillates between 1 minus a and 1 plus a. So for the phase, I have this again. Let me, for the phase, okay. For the phase, let me fix this. So for the phase, let's draw this. So it is just like this. So for minus pi, for 0, and for plus pi, actually it is a real number, so phase is 0, so this is angle of x of omega. And the peak value is at, let me, P1 and P2. So P1 is nothing but the maximum value is tangent inverse a over square root of 1 minus a squared, and P2 is nothing but minus P1. So it simply oscillates in between those values. You can check this by yourself. Actually, it is easy to calculate the phase. So it is tangent inverse a over square root of 1 minus a squared is the maximum value, and you have the negative of it as the minimum value. So this is for minus pi over 2. So this is for pi over 2. So the next example is your actual exercise. Please try this at home. I will solve the next one. I have impulse response of a discrete time LTI system, which is given as h of n is equal to impulse of n plus 1 plus 2 impulse of n plus impulse of n minus 1. Compute and plot h of omega, which is called the frequency response of the LTI system. So the frequency response is nothing but the Fourier transform of your impulse response. So it is easy to calculate. X of omega is actually h of omega is summation h of n h bar minus j omega n from minus infinity to plus infinity, and this equals to summation n from minus infinity to plus infinity impulse of n plus 1 plus 2 impulse of n plus impulse of n minus 1 times h power minus j omega n. So I will use the shifting property. So I will evaluate this at n equals minus 1, n equals 0, and n equals plus 1. So this is non-zero for n equals minus 1. This is non-zero for n equals 0, and this is non-zero for n equals plus 1. So I will put all of those values. This is h power j omega plus 2 plus h power minus j omega. And it's nothing but 2 plus 2 cosine theta. So it is a real number. So if you want to plot this, let me plot here. It is something like this. So this is minus pi, this is plus pi, this is 4 maximum value, this is 2, and this is 0. And of course, this is periodic with 2 pi. So also this is periodic with 2 pi, this is periodic with 2 pi. So they are all actually periodic with 2 pi. So this is the case. Next example is about a rectangular pulse. It is defined as 1 for n1, for n is in the interval plus minus n1. So compute x of omega plus its magnitude and phase. So first let me draw x of n. So this is my x of n from minus n1 to plus n1. So x of omega is simply summation n from minus n1 to plus n1 e power minus j omega n. If you let m is n plus n1 or n equals m minus n1, then in this case summation is simply so x of omega is simply m from 0 to 2n1 e power minus j omega m minus n1. So I put m minus n1 instead of n. So this is equal to summation m from 0 to 2n1 e power minus j omega m e power j omega n1. So this does not depend on m, so it simply goes out e power j omega n1 summation m from 0 to 2n1 e power minus j omega m. So this is equal to e power j omega n1 1 minus e to the power minus j omega 2n1 plus 1. So previous week I have actually explained to you this evaluation. So if you put everything to let's say j omega n1 to e to the power minus j omega n1 over 2 over 1 over 2 over e to the power minus j omega over 2 parentheses, what you have is this. You have e to the power j omega n1 plus 1 over 2 minus e to the power minus j omega n1 plus 1 over 2. So plus minus this term over e to the power j omega over 2 minus e to the power minus j omega over 2. So actually what I do is this. I divide this term by 2 and take the parentheses. If you divide this term by 2, what do you have? E to the power minus j omega n1, so those two cancel, plus 1 over 2. So this is my parentheses. And what I will do, there is a 1 here. So this is the 1 with the plus. So if you multiply this one with this one, you have 1 minus this minus term minus this times this time. So they're the same, right? So it's squared. So you have the second term. Similarly, I divide simply this term over 2. If you divide this term over 2, you have e to the power minus j omega over 2 parentheses, and you have the plus version here, and you have the minus version here. This time this is nothing but this 1 here. This time this is nothing but e to the power minus j omega. So if you go further, this is sine omega n1 plus 1 over 2 over sine omega over 2, and this is nothing but, you know, the Euler's relationship. E to the power minus something minus e to the power minus something is sine, so 2j sine, 2j's cancel out, so you have sine over sine. So again, this is a purely real number. So this is the plus of x of omega. So this is sine over sine. If you plot this, it is something like this. So next thing that we will discuss is actually the response of LTI systems to complex exponentials. Remember, z to the power n is an eigenfunction of discrete time LTI system, and the eigenvalue is given as h of z. So if you have z to the power n, if you have z to the power n as the input to an LTI system defined by h of n, at the output you have h of z times z to the power n. this z to the power n is the eigenfunction, h of z is the eigenvalue. So the output is nothing but z of n multiplied with some numbers, which is h of z. So if z has a magnitude of 1, it means that z is equal to e to the power j omega like, then the complex exponential z to the power n e to the power j omega n and its eigenvalue reduces to discrete time Fourier transform. So this is simple. Instead of z here, you have z equals e to the power j omega. If z equals e to the power j omega, then h of z evaluated at z equals e to the power j omega is nothing but the discrete time Fourier transform of your signal, h of n. So by the way, this is called as the z transform, and we will not evaluate this in this course, but this is a special transform called as the z transform. So this is just for your side information. So here I have a simple example. Let x1 of n is equal to cosine pi over 4n. x2 of n is cosine 3 pi over 4n. So they are the inputs. You are asked to find the corresponding outputs y1 and y2 of n, and h of omega is given as rect of omega over pi. So what does it tell you? So remember, the rect signal is, so this is non-zero. The rect is non-zero whenever minus 1 over 2 smaller than omega over pi smaller than 1 over 2. So if omega is in the interval from pi over 2 to minus pi over 2 to plus pi over 2, this is non-zero. Otherwise, it is simply 0. So what is this? If you plot this h of omega from minus pi over 2 up to pi over 2, it is non-zero, and it is 0 elsewhere. Of course, I will plot from pi to minus pi, and it is, let's say, periodic with 2 pi. So this is periodic with 2 pi. It means that at omega equals 2 pi, it is again here signal. Okay, it is periodic with 2 pi as every discrete time Fourier transform signals. So what is my x of n? So let's write x1 of n as 1 over 2 e to the power j pi over 4n plus 1 over 2 e to the power minus j pi over 4n. If this is input to your system defined by h of n, at the output I have 1 over 2 h of omega evaluated at pi over 4 times e to the power j pi over 4n plus 1 over 2 h of omega evaluated at minus pi over 4 times e to the power minus j pi over 4n. So this is nothing but the eigen function. This is the eigenvalue. Okay. So you have exactly as in here. Okay. The output is the input itself. So the input itself multiplied with the eigen function, eigenvalue. Again, the second output is itself here. It is itself here, 1 over 2 times e to the power minus j pi over 4n times h of omega evaluated at omega equals pi over 4. So what is the value at pi over 4? This is pi over 2. So at pi over 4, h of omega is 1. So this is equal to 1. This is equal to 1. So y1 of n is nothing but x1 of n. So that's it. y2 of n is your homework exercise. So please try this at home. So what about discrete time Fourier transform of periodic signals? Well, in continuous case, remember they were impulsive, right? So if I have x dot t represented as ak e to the power jk omega 0 t, so in Fourier series form, from this I can easily find the corresponding Fourier transform, because I know that e to the power j k omega 0 t and 2 pi impulse omega minus k omega 0 are Fourier transform pairs. So that's why I can easily find the Fourier transform, continuous time Fourier transform for continuous time periodic signals. Well, in this case, actually, the discussion is similar. Here I have x tilde of n, which is written in Fourier series form as ak e to the power jk 2 pi over n times n. Remember, this k runs over n values, capital N values, because AKs are periodic. So I only need capital N or period many values to represent my x tilde of n. So if I take the Fourier transform, this is what I have, e to the power jk 2 pi over n times n, and this 2 pi times impulse are Fourier transform pairs. So this is what I will show in a moment. So in continuous case, remember, e to the power j omega 0 t and 2 pi impulse omega minus omega 0 were Fourier transform pairs. And in discrete case, e to the power j omega 0 n and summation L 2 pi impulse omega minus omega 0 minus 2 pi L are Fourier transform pairs. Actually, this summation over L and 2 pi L are actually due to, let's say, periodicity with 2 pi. So discrete time Fourier transform must be periodic with 2 pi. So this is why there is a summation, and the terms are shifted by 2 pi L amounts. So if I find x of n corresponding to this signal, what I will do, I have 1 over 2 pi integration over a 2 pi period x of omega e to the power j omega n d omega, and this is nothing but 1 over 2 pi integral from 0 to 2 pi. So I'm assuming that omega 0 is, of course, positive. So it is 2 pi impulse omega minus omega 0 e to the power j omega n d omega. And by using shifting property, those cancel out. I will put here simply omega 0, and this is e to the power j omega 0 n. So this is my discrete time signal, and this is actually the discrete time Fourier transform pair, e to the power j omega n and actual 2 pi impulse omega minus omega 0. So you can for sure tell that e to the power j omega 0 n and 2 pi impulse omega minus omega 0 are Fourier transform pairs, but this is, you should specify, mention, write that this is periodic with 2 pi. So if you write this, you do not need those actual summations and shiftings, because this summation and shifting is to make this signal periodic. But you specify that if it is periodic, then you do not need to write this summation term. So if you go further and write your x tilde of n, summation k from 0 to n minus 1, a k e to the power j k 2 pi over n. Well, note that I started k from 0, but it's not necessary. I can start it from k equals k0 from any k0 value. So x of omega is nothing but summation k from 0 to n minus 1, a k Fourier transform of e to the power j k 2 pi over n. So I have obtained the Fourier transform of this one. So Fourier transform is a linear operator, so that's why summation and ak are out of the Fourier transform. So I only find the Fourier transform of the term which contains n, of course. So this is equal to summation k from 0 to n minus 1, a k summation L from minus infinity to plus infinity 2 pi impulse omega minus 2 pi over n k minus 2 pi L. Okay, this is my, remember from previous flight, this is 2 pi impulse omega minus omega 0, but it is made periodic with 2 pi by shifting in 2 pi amounts. So this is equal to, let's write summation k from 0 to n minus 1, summation L from minus infinity to plus infinity, a k 2 pi impulse omega minus k 2 pi over n minus 2 pi L. Okay, so this is nothing but, if I write from k 0 to n minus 1, a k 2 pi impulse omega minus k 2 pi over n, but periodic with 2 pi. So I have omitted this term here and this summation and specify that it's periodic with 2 pi. Those terms are to make this periodic with 2 pi. So if I specify that it's periodic with 2 pi, I do not need them. So this is in a more compact form. So here in summary, first you determine the Fourier series, discrete time Fourier series coefficients ak, then simply write it as in this form. So that's all. Actually here k runs from minus infinity to plus infinity. Actually AKs are periodic. So since AKs are periodic, the signal from k running from minus infinity to plus infinity is also periodic. So you can use the either way. Either use this double sum form or use this simple k from 0 to n minus 1 and specify that it's periodic with 2 pi, or you can use this form, whatever you wish, because since AKs are periodic, this is also periodic. So a simple example, cosine 2 pi over 5n, find its discrete time Fourier transform. So x tilde of n is cosine 2 pi over 5n, and it's equal to 1 over 2 e to the power j 2 pi over 5n plus 1 over 2 e to the power minus j 2 pi over 5n. So this is a1, this is a minus 1, sorry, this is a minus 1. And this equals, of course, summation k a k e to the power j 2 pi over 5n. So what about x of omega? So by the way, let me write x of omega. It is summation k from minus infinity to plus infinity 2 pi a k impulse omega minus k 2 pi over 5. And I use this notation and specify that a1 is equal to a minus 1. This is 1 over 2, a minus 2, a 0, and a plus 2 is 0, and a k is equal to a k plus 5. So n is 5 for the signal, so a k's are periodic with 5. So I only write a0, a1. So if I start from minus 1, I write, sorry, from minus 2, I write a minus 2, a minus 1, a0, a1, a2. So 5 terms are needed, okay? I only need 5 terms starting from minus 2 and say that the rest are ak equals ak plus 1. So those two actually bubbles are defining all of my ak coefficients since n equals 5. So if you want to plot this, what does it look like? So let me write here, plot here. This is my x of omega. Here I have a 2 pi over 5 minus 2 pi over 5. I have an impulse with amplitude pi. And this is, let's say, pi. This is minus pi. So of course, this is periodic with 2 pi. So this is periodic with 2 pi. It means that at 2 pi, I have such two impulses. Okay, one of them is at 2 pi over 5 plus 2 pi, and the other is at 2 pi minus 2 pi over 5. So this is periodic with 2 pi, my x of omega. The next example is about discrete time impulse train. So you know that this is impulse train. So impulse of n is shifted by capital N amounts. So AK is simply 1 over n, summation n over n, x of n e to the power minus j k 2 pi over n. So this is equal to 1 over n, summation impulse of n e to the power minus j k 2 pi over n. Of course, this is nothing but 1 over n. So x of omega is simply summation k from minus infinity to plus infinity 2 pi over n impulse omega minus k 2 pi over capital N. So this 1 over n is nothing but AK. Okay, 1 over n is nothing but your AK. Well, we will stop here at properties, and next week is our last week. So next week I will continue with the properties of discrete time Fourier transform. So